ಈ ಸಭೆಗೆ ನಮಸ್ಕರಿಸಿ ಡಾಕ್ಟರ್ ಎನ್ ಅವರನ್ನು ಸ್ಮರಿಸಿ ನಮ್ಮ ಕಲಾಪಗಳನ್ನು ಆರಂಭ ಮಾಡ್ತೇವೆ. Now I call upon to the stage Dr. N. Subramania, President, National Education Society, the host of the event. Professor Umesh Wagmare, President of Indian Academy of Sciences. The luminary of today's event, Professor Subir Sachdev, the Raman Chair Professor. Shri Venkateshwar Reddy, Honorary Secretary of the National Education Society. Dr. Y.C. Kamala, the Principal, also the host of today's event. And Madam Sucharita, Secretary of the Bangalore Science Forum. So with that, now I request Shri Venkateshwar Reddy, Honorary Secretary of NES, for the welcome remarks.
Hello, namaskara. Ladies and gentlemen and esteemed guests, it is with a great pleasure that I stand before you today to extend warm welcome to this distinguished gathering. Founded in 1917 by the visionary theosophist Annie Besant, the National Education Society has been beacon of education enlightenment, overseeing the 21 institutions, primarily in rural areas, aiming to bring light of the knowledge to every corner. Under the guidance of the NES, by the strong will of Dr. H. Narasimhaya, the Bangalore Science Forum emerged in 1962, dedicated for the science communication and to bridge the gap between the science and the common man. Over the years, this forum has played a crucial role in sparking throughout conversation. It has arranged thousands of talks, movie screening, and summer learning sessions, contests, and science festivals. These efforts have greatly helped make science more accessible and widely appreciated. Today, we are honored to have with us Professor Subir Sachdev, a luminary in the field of physics from Harvard University, who will share insights and quantum entanglement in nature. His presence adds immense value to our commitment to fostering scientific understanding. I welcome you, sir. A heartful welcome is also extended to our esteemed President, Dr. N. Subramania, whose leadership has been instrumental in steering NES towards the greater heights. I welcome you, sir. We are pleased to have Professor Umesh Wagmare, President of the Indian Academy of Sciences, guiding the proceedings of today's event. I would also like to welcome another distinguished office bearers of Indian Academy of Science and Academy Trust, NES, and the Bangalore Science Forum to this gathering. Lastly, a warm welcome to each one of you present here today. Your presence reflects the shared passion of knowledge and commitment to the noble cause of advanced education and scientific awareness. Let us collectively embrace the intellectual journey that awaits us. Thanking you.
Thank you, sir. Now I request Professor Umesh Wagmare, President, Indian Academy of Sciences, to introduce the speaker and also to moderate the session.
Thank you, Mahesh. Good afternoon, all. The Indian Academy of Sciences and the Academy Trust are delighted to join hands here with the National Science College and also Bangalore Science Forum to host the public lecture today by Professor Subir Sachdev, who is visiting as the Raman Chair Professor of the Indian Academy of Sciences. Indian Academy of Sciences was founded in 1934 by Sir C.V. Raman to promote and uphold the cause of science with a strong commitment to society. The Raman Chair was instituted in 1972 after C.V. Raman passed away in 70 by the Government of India in memory of Sir C.V. Raman. Highly accomplished and eminent scientists are invited by the Council of Indian Academy of Sciences to occupy the Raman Chair and connect with the Indian science community and society. I'm absolutely delighted to have Professor Subir Sachdev with us in this capacity. He has a strong connection with India and, of course, in particular with Bangalore as well. Professor Subir Sachdev was educated at St. Joseph's Boys High School in Bangalore, Kendriya Vidyalaya in Bangalore, Indian Institute of Technology in Delhi for 1 year, and then he transferred to MIT for his bachelor studies. And then he completed his PhD in physics at Harvard University, and currently he is Herschel Smith Professor of Physics at Harvard University. Subir has been elected to National Academies of Sciences in India as well as United States, and is also a foreign fellow of the Royal Society. He is a recipient of several awards. I must mention a couple of them: the Dirac Medal from the International Center for Theoretical Physics and Lars Onsager Prize from the American Physical Society. Professor Sachdev's research describes the connection between the observable properties of matter and the nature of quantum entanglement in many particle wave functions. It will take a long time to give a full introduction to Professor Sachdev and his accomplishments, but his work is published in very standard textbooks authored by him. One is Quantum Phase Transitions, and another book, Quantum Phases of Matter, published by the Cambridge University Press. I think there's one aspect of Professor Sachdev I must highlight. I think one of the most inspiring things about Professor Sachdev is his research has spanned 35 years of really hard work and dedication to tackling some of the hardest problems. In fact, motivated by some very puzzling observation in the context of high TC superconductors. And the accomplishments came his way, uncovering deep connections between different aspects of physical world and physics. I won't take much longer. It's a pleasure to have you, Professor Sachdev. And he will talk to us about quantum entanglement in nature, superconductors, and black holes. Over to you, Subir.
Okay, I use this mic here, right? Okay. Well, thank you very much, Professor Wagmare, for that very kind introduction. It's really an honor for me to be here at this very distinguished chair established by the Government of India, and especially, sorry, you can't hear me? Mike? Okay. Yeah, okay, there we go. That's better. Okay, yes, that's probably a bit too loud. Okay. Is that okay? Yeah? All right. Okay.
Is it fine to use?
Yeah, it's fine. Okay, great. What was I saying? Yes, so I'm really honored to be here, especially in a chair named after one of India's and in the world's great scientists, Professor C.V. Raman. And thank you very much for the very kind hospitality. So as Umesh mentioned, I am actually from Bangalore. I grew up in ITI Colony. Maybe there's somebody from ITI Colony here. I don't know. And growing up, I heard a lot about National College, and several of my friends went to National College, but this is the first time that I'm here at National College. So, all right. So let me get started. So the title, as announced by Umesh, is Quantum Entanglement in Nature, Superconductors and Black Holes. So I think this is a very varied audience. So what I've decided to do is just highlight, give you a brief history lesson, just reminding you about 4 great discoveries in physics, none of which have anything directly to do with me, but they're connected to topics that I've worked on and will help explain the ideas I want to get across. So these topics are the basic idea of entropy, which is rather deep and very important for many applications in physics. Then superconductivity, I'll explain what that is if you don't know. Black holes, which is in 1916. And you'll be very surprised, to hear a talk where somebody's talking both about superconductivity and black holes. And that's really the main message of my talk, that there is actually some deep questions in physics which are very common in very different physical phenomena. And the link that ties them all together is quantum entanglement, which one can say was at least postulated theoretically in 1935. All right, so let me begin by just defining entropy and temperature in very simple terms. So the idea of entropy really came about from engineers like Clausius in 1865, and the basic observation that people were trying to systemize, that there are no perpetual motion machines. I don't know if you can see the little, I think you all know what Simpsons are. So this Mr. Simpson's daughter, Lisa, has made a perpetual motion machine. Instead of being proud of his daughter, he says, "You're violating the laws of thermodynamics." So the fact that there are no perpetual motion machines, I'm hearing an echo. Is it okay? Yeah. Is it okay now? Is that better? Was encapsulated by Clausius in the idea that every system has some quantity they call entropy, which could not decrease. Okay, so that's the origin of it. But the connection to, and then temperature was something you just measured with a thermometer. So you made an arbitrary scale, degrees Kelvin or degrees Celsius or whatever you want, and then you have something called temperature. But the fact that entropy and temperature are something very fundamental and have some deep connection to the microscopic constituents of matter was made by Boltzmann in 1870. So this is his tombstone in Vienna, and written on it is this very famous equation, S equals kV log W. S is entropy, kV is Boltzmann's constant, and then W is Boltzmann's innovation. He's connecting entropy, a macroscopic thermodynamic quantity, to something microscopic. So in 1870, people didn't even know for sure about what matter was made up of. They didn't know that the air in this room was made up of molecules of oxygen and nitrogen. What the size of the molecules was not known. But Boltzmann boldly proposed that was the case. And W was a measure of the uncertainty in the positions and momenta of the molecules. So he had some way of defining the randomness or the uncertainty in the positions of all the molecules. And so this was his famous insight, that a thermodynamic quantity was connected to really the microscopic nature of matter itself, which obeys, in his time, Newton's laws of motion. And from this famous relation, he could derive many of the principles of thermodynamics. So that's entropy, and you have to remember this famous relation, which is on Boltzmann's tombstone. And what is temperature? Well, from these work of Boltzmann and others, you could now relate temperature to the rate of change of entropy with energy. So I'm using equations here. I don't know the level of the audience, but nothing is more complicated than an equation the rest of my talk. So if you don't, I've explained in words what these equations mean too. All right, so that's entropy and temperature and the famous equation of Boltzmann. All right, so now let's move on. Let's talk about superconductors and ordinary conductors, sometimes often called metals. So what's an ordinary conductor? Well, it's a metal like copper, which conducts electricity very easily, and it's in all your iPhone devices and everything else. And a semiconductor, well, it's half a conductor because it doesn't conduct as well. And that's also absolutely essential ingredient in any electronic device. Well, a superconductor, okay, that's not what a superconductor is. Superconductor is something somewhere where the electricity flows without any resistance. So in copper, it's single electrons flowing in a copper wire. But superconductivity was discovered in 1911 and by Camille, and what he did was he built a big, huge refrigerator, which you can see if you go to Leiden in the Netherlands. And he discovered that if you cooled it down to this very low temperature, mercury would conduct electricity with zero resistance, exactly zero resistance. So that was a very exciting discovery because when you have the ability to conduct electricity with zero resistance, you can pass a lot of current and do a lot of interesting things with it. But the price you had to pay was that you had to cool things down to a very low temperature. So that's when we were all very excited when in 1986, there's a whole new family of superconductors discovered, sometimes called the high temperature superconductors. Because if you just took a little pellet of this material, for example, yttrium-bearing copper oxide, and you could put it in liquid nitrogen is something that can easily create, it goes superconducting. So here's a demonstration of a superconductor. So that's a little pellet of yttrium-bearing copper oxide. It's been dipped into some liquid nitrogen in here. And these are a bunch of ordinary magnets. And so now you can see in the movie, the superconductor just floats above the magnets until it heats up, and at some point, it just collapses on the magnets. So what's happening here is that the superconductor has the ability to conduct current without any resistance and quite easily. So as a result, it creates a magnetic field which keeps it floating above the field created by the permanent magnets. All right, so that's really the fundamental use of superconductors, is that they can create very strong magnetic fields. And that brings me to probably the most exciting application of high-temperature superconducting magnets, which is application in fusion energy. So fusion is a way of creating energy where you take nuclei, like hydrogen or deuterium and tritium, and you fuse them together. Now, to make that process happen, you have to compress these nuclei in a very small space, and typically use magnetic fields to do that. And there's been a traditional way of building these fusion machines that's very big and expensive, but there's some exciting new ideas. This is a Commonwealth Fusion System is a company, startup company in Massachusetts, and there are many others around the world. And they're using precisely this high-temperature superconducting material to create fusion energy, which potentially is completely green. It doesn't have at least any CO2 waste. Anyway, who knows whether this will work? But if it did, I think it will certainly make me feel a lot better because my lifetime of work on superconductivity would have been worth it. So I think this is a really exciting goal, and the potential is also quite reasonable. All right. So here's a little bit more information about this superconductor. So what I have here is the density of electrons in this crystal, which you can change by changing the oxygen concentration versus temperature. And of course, you find it's a superconductor over some region of density and temperature, with a critical temperature of about 100 Kelvin, which is above the boiling point of liquid nitrogen. And so what we'd really like to do to make this superconductor very, very useful is to take this TC and make it, well, maybe up here to, room temperature is 300 Kelvin, let's say. And so that's where, a microscopic understanding of what's causing the superconductivity is really crucial. Can you microscopically understand why this TC is 100 Kelvin? Just like Boltzmann could microscopically understand the properties of the gas in this room through some simple assumptions on the properties of the molecules. Well, the answer is we don't. We don't understand today. And that is one of the big questions that's certainly driving my own research. In particular, a natural question to ask is, well, if this thing is going superconducting, you really need to know what it came from, what was above the superconductor. So if you look out here where TC this critical temperature is quite low, so it's not as interesting, you find that this material behaves like what we call an ordinary metal, just like copper. You measure its properties, it's not so different from copper. But in between, we have this regime called the strange metal, but it doesn't look like copper at all, and it has some rather bizarre properties, which I won't go into in any detail. But understanding those bizarre properties is really the key then to understanding when this system would go superconducting. And so I'll say a bit more about what's needed to understand those bizarre properties. And as you'll see, what's needed is quantum entanglement. Okay, so one of the bizarre properties for the experts is if you measure the resistance as a function of temperature, it's a very linear function of temperature, and that's not something you see in a material like copper at such low temperatures. All right, so that was topic Great Discovery 2, which was discovery of superconductivity in 1911, which led to many, many developments, and I just told you about one of them, some very basic problems in physics that are really crucial for important applications like fusion energy. Okay, so black holes. This is now I'm going to go somewhere else. I'm going to go out in the universe and talk about very big and very compact objects. So what is a black hole? Well, this is one of the great triumphs of theoretical physics. A black hole was actually predicted in 1916 by Karl Schwarzschild in Germany, who then died very soon after in World War I. And Karl Schwarzschild was working then with the very newly developed theory of gravitation from Einstein. And he found that there was a solution of Einstein's equation which had these very bizarre properties. So he asked the following question. Suppose you take some mass m, g is Newton's constant, c is the velocity of light, and r is what we call the Schwarzschild radius. So if you take a mass m and you compress it to a size smaller than r, what Schwarzschild discovered was that such a compressed object has a gravitational force that's so strong that light itself can never escape. So this is r, this is the radius r, that's what we call the horizon, and inside is some very dense matter, and its gravitational attraction is so strong that light, if any atom emitted a beam of light, it will just turn around and come back. It will never escape. So there would be no signal whatsoever of anything that could ever come out of this region of the universe inside the horizon. All right, well, so this was what Schwarzschild and I think pretty soon after many others realized, but nobody really took this seriously for a long time. In fact, all the way up to the 1960s, where after the work of Chandrasekhar and also Oppenheimer, people started believing that such a strange object could actually exist and be out there. In particular, just to appreciate how dense this matter is, if you put in the mass, the Earth's mass, just put it into this equation, R you will get is 9 millimeters. So you would have to take the entire Earth and compress it down to a size of a pea to make the Earth into a black hole. Seems totally unreasonable. Why would anything ever do that? Well, it turns out there in our universe, there are such objects. I'll come to that in a minute. I forgot about this. But it's actually even stranger than that. So now you can ask, okay, you have this very compressed matter inside the horizon. What is it doing? Well, if you take Einstein's equations, you find something even stranger. The point is that gravity, unlike electrical forces, is always attractive. Gravity just always attracts. So you have this dense matter inside the horizon. It's not as if it stops compressing. It continues to collapse. And it will collapse down to a point of infinite density. So at this point, surely, when your matter is so dense, and where the density is infinite, we cannot believe Einstein's theory of gravity. We have to really ask, what is the theory at the very short distances? And the theory we know today is the quantum theory. So you really have to apply the quantum theory to figure out what's happening inside a black hole. Even though this could be a huge object out there, inside, you can't understand it without quantum mechanics. So in that sense, there's some connection to superconductivity, in a very loose sense so far. Even for a superconductor, it's a big object in holding a hand, but its fundamental properties rely on understanding something about quantum mechanics. So this singularity convinced many that black holes were unphysical solution of Einstein's equation and did not exist in our universe. And anyway, okay, but now we know that black holes are everywhere. They're just through various advances in astrophysical observation, including the LIGO telescope, of one of which is being built in India now. We know there are black holes in every galaxy, quite a few of them. And in fact, at the center of every galaxy, including the Milky Way, which is our galaxy, there's what's called a supermassive black hole. This is an actual picture of it just from the last year. This is the horizon around it and light bending around it. Of course, we can't see inside. So the supermassive black hole is not Earth's mass. It's 4.3 million times the mass of the sun. And if you put that expression into Schwarzschild's relation, you will get a radius of 10 to the 11 meters, which is about the distance of the Earth from the sun. So it's a gigantic object, 93 million miles or 100 million miles, which is as dense as the Earth compressed to the size of a pea. In fact, probably even denser. And it's at the center of every galaxy, including our galaxy. And so there's a lot of exciting work in trying to measure all of this, at least the predictions of Einstein's equation. But as I said, there's this singularity at the center, and we needed quantum theory to understand what's happening inside a black hole. This is quite an urgent question because it's right there. You can see it in the sky, so we should understand what's happening at the center of our galaxy. Okay, so the first person to really start thinking about applying quantum mechanics to a black hole was Stephen Hawking. And Hawking had this very bold idea that you could understand something about a black hole without knowing too much about the inside. I mean, we still don't know much about the inside of a black hole. But he had the idea that you could be outside a black hole, and even from the outside, you could see some quantum effects. So this was a brilliant idea. Again, of course, at that time, many people were surprised by it and skeptical, but today we know that Hawking was completely got it right. And what he concluded by applying the principles of quantum mechanics to a black hole, that every black hole has an entropy and a temperature. And like any hot object, they will evaporate, like any cup of coffee eventually, which is hot and it's radiating, it's at some temperature, and it will slowly evaporate and disappear. And Hawking even computed, without knowing what's inside a black hole, what we call the Hawking temperature. And it involves the quantities I've already introduced, the velocity of light, Newton's constant, the mass of the black hole, Boltzmann's constant, and h bar is Planck's constant. So this is one of the amazing formulas in physics where all the fundamental constants kind of come together. Planck's constant I haven't introduced yet. It's a basic constant in quantum theory, which I'll get to in a minute. Anyway, this is a picture of Hawking's gravestone. So this is the second famous equation in physics, which is written on a gravestone. Boltzmann being the first, of course. And this is in Westminster Abbey. And it says, here lies what was mortal of Stephen Hawking. And there's Hawking's formula right there. In fact, I was in London this summer, and I tried to go and see this. But the line was way too long. I couldn't wait. So this picture is from Wikipedia, but maybe next time I'll get an actual picture of Hawking's gravestone. All right. So I've told you about superconductors and some really key open problems in theory of superconductivity. I've told you about black holes and the fact that, they're absolutely real, they're out there, but we have no understanding really, apart from Hawking's formula, until recently, I would say, of what's inside a black hole. How do we understand this object, which is so dense that quantum mechanics must play a role? So it turns out there is a link of ideas that are important for understanding these questions. And the idea is really quantum entanglement. So that's the fourth great historic advance in physics that I want to now describe. So I presume you've all heard of quantum mechanics, at least a little bit. And maybe you've heard about a cat that can be both alive and dead. And so the nurse is giving this person, Mr. Schrodinger, who came up with the Schrodinger equation, and that with good news and bad news. Okay. But so what is, can you really make a dead cat and a live cat at the same time? In principle, yes, some loose sense, but only if you completely disconnected the cat from everything else in the universe. Well, if a cat was completely disconnected from the universe, it would have no oxygen to breathe, so it would be dead anyway. So this is just a purely hypothetical statement that people can remember. But what this encapsulates is a fundamental new idea in quantum mechanics, which is the theory of the very microscopic. So, Newton came up with Newton's laws that describe the planets, how the planets move around the sun. And then you can ask, well, if you make objects smaller and smaller and smaller, do Newton's laws still apply? And what physicists learned by the turn of the century, in 1910, 1920, was that when you got down the size of an atom, like a hydrogen atom, Newton's law did not apply. And there was a new quantum theory developed to understand the motion of a single electron around a single proton in a hydrogen atom. So it's a long way from a single atom to a black hole, but that's what we're going to try to do. And this theory, which has been extremely successful, despite very, very clever attempts to destroy it, it's withstood all the tests of time, so I'm not going to go through all of that. So I'm just going to ask you to accept, there's no doubt the quantum theory is correct. And what this theory introduces is a fundamental new idea, which did not exist at all in the Newtonian view of the universe, which is the idea of superposition. That's the dead cat plus live cat, which means that a physical system can be really in two or more distinct states at the same time. That's a very crude way of saying it. There's a more precise mathematical way of expressing this. And this is something we just have to accept. Once we accept the basic theory of the hydrogen atom, for example. So there's a very famous experiment called the double slit experiment, which illustrates this. So you have some electrons coming out one by one from this source, and they go through these two slits. And Schrodinger's equation tells us that they behave like a wave that's going through both slits. And if you have a wave going through both slits, you get this so-called interference pattern of light and dark. But if you're detecting the electron, even one electron comes out, you will see one blip at some definite location. So at that point, you would say, well, if I saw a blip here, probably that electron came through this slit. And if I saw a blip here, maybe it came through this slit. But you would be wrong, because After you see many, many blips, you find that the distribution of the electrons here does not obey what you would expect of electrons coming either through here or here. Rather, it obeys what you expect from waves coming through both slits and interfering with each other. So the way we say this, and this is really the one equation I need to get across, we talk about a state of a system or state of an electron. So there's a state of an electron, which we call L for an electron going through the left slit. And there's a state of an electron, R, for an electron going through the right slit. And the superposition state, which explains this experiment, is some kind of sum of both. So the electron can superpose two very distinct states. Okay, all right, so this, so electrons are weird things. Nobody's ever really seen an electron. Maybe they do this bizarre thing. And so people slowly started accepting this in the 1920s, 30s. But one person who really thought this couldn't be right is the world's most famous scientist, which is Albert Einstein. And in 1935, he wrote a brilliant paper with Podolsky and Rosen, which is titled, Can Quantum Mechanical Description of Physical Reality be Considered Complete? And it's clear if you read the paper that his view of the answer was no. And that, in fact, quantum mechanics was missing what sometimes are called hidden variables that characterize each electron, for example. And once you knew those hidden variables, you wouldn't need this ridiculous principle of superposition. He didn't use those words, and suggesting what he might be thinking. But this paper, like many great papers, even though it was skeptical, it was on the right track, and it presented an interesting thought experiment. Not exactly this way, but this is the modern update of it. So Einstein, the EPR said, okay, it's fine. Maybe a single electron can be in one or two distinct states. How about two electrons? So quantum mechanics said, no, yes, absolutely. Not just single electrons, but pairs of electrons can also be in superposition states. And this is what quantum entanglement really is. It's about superposition of many electrons. So let's start with two. So if I take a hydrogen molecule, this is a highly simplified view of a hydrogen molecule. It has two protons and two electrons. And I just represent each electron, whether it's spinning clockwise or anti-clockwise, by an up or down arrow. And so one possible state of the two electrons in a hydrogen molecule is the left electron is up and the right electron is down. Now, people who are solving all of Schrodinger's equations for a hydrogen molecule know that's not the right answer. The correct answer is that it's actually in a superposition of two states. The left electron up, right down, minus, well, for mysterious reasons, the opposite orientation. So it's what we call the two electrons are entangled. That is, the spin of one is entangled with the spin of the other, but neither of them is either up or down. The answer is they're really both, but in a very interesting correlated way. All right, so EPR said, well, okay, fine, this is your theory of a hydrogen molecule, but now imagine that you could separate the two electrons without disturbing their spin. So you would have one electron here in Bangalore and the other electron in Delhi in a very, very careful experiment. And quantum mechanics would say that as long as you didn't disturb their spin, okay, in principle that's really impossible, but in principle it's possible, okay. They're still entangled. So this means that the electron in Bangalore, if its spin is up, if you look at it and spin is up, the other electron is spin down, or vice versa. And that's the way it is while you move them really far apart. Okay, so I have this electron here in Bangalore. My friend has their electron in Delhi. And then I look at my electron. And at that point, I'm going to see either up or down. Just like when I did the double slit experiment, I just saw a single blip somewhere. It wasn't everywhere, so you just see some particular state. So I see my particular electron to be down. And then I know that my friend's electron in Delhi must be up. Now, so this seems like action at a distance. What I'm doing here is instantaneously determining what's happening in Delhi. But it's more subtle than that, because while I'm measuring this electron and see it to be down, my friend in Delhi has no idea what I've done. My friend will do their own experiment, and they will see up or down. It's only later we can call each other and verify that our measurements were uncorrelated. And it's only at that point some information travels. So there's not really any information traveling instantaneously. But Einstein said, no, this is not good, and he called it, it's said that he called spooky action at a distance. Now, I never believed that he couldn't have said that. But in fact, I discovered past summer he did. He wrote a letter in 1947 to Max Born in German, and I've just translated here. So, spukhafte Fernewirkungen, apparently that's spooky action at a distance. So he said, Einstein says, I cannot seriously believe in it being quantum mechanics, because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky action at a distance. So how do we, okay, fine. This was a thought experiment, and maybe Einstein was onto something. But today, there's no doubt at all. These experiments have actually been done. They're not just a thought experiment. This is an article from the New York Times in 2015 with photons. So you do it with light, not with electrons. With light, it's much easier to move photons of light far apart without disturbing their polarization. They have counterclockwise and clockwise correlation, and there's a similar correlation of the polarizations as there is for the spin of the electron. And this was, 1.3 kilometers apart. Today, you can do it up to a satellite. I mean, this experiment has been repeated thousands of times. So spooky action is real. So the word's a bit misleading, though, because it suggests that something is non-local about physics or some kind of violation of causality. But there isn't really. But what the really new idea we have to get our heads around is what's not local. Everything about physics is local. What I do here only influences what's near me. It's really, nothing travels faster than the speed of light. But what I have to accept that the idea of a quantum state, which is kind of an intermediate concept in computing results of experiments, is not local. That is, when my electron here and my friend's electron in Delhi share the same quantum state. The reason they share the same state, or they're in a superposition of the same state, is because in the past, they were both together, and they interacted locally. You just separated them, and they keep the memory of that state. And then you have to accept that the state is non-local. It's not any particular place. I don't own the state. My friend in Delhi doesn't own the state. It's not in any particular place. So once you get used to that idea, then this stops being less spooky. But it's real, of course. It has to be less spooky because it is what observed, millions of times. So in fact, this particular type of experiment is the basis of quantum cryptography, where you can transmit information not faster than the speed of light, but in principle very securely. But I'm not going to go into that. All right, so that's the end of my introduction to the 4 great ideas in physics. And I have about 20 minutes, is that right? I think I could maybe take 1 or 2 questions at this point if there's somebody really wants some burning question on that. Maybe for someone, students back there, yeah. Yeah, please go ahead. ER equals EPR. Okay, that's a very modern idea, which I will say something about, not quite, later. Yeah, that has to do with black holes, in a sense, and I'm coming to that, so I'll defer that question. I want questions about what I talked about.
Does the parity of the time reverses at the center of the singularity of the black hole?
Does the what?
Parity of the time, direction of the time.
No, no. I mean, time is, of course, it's hard to define what is space-time at the center of a black hole, but nothing's going backward in time, no. Okay, one more last question here.
Regarding the entanglement,
Yeah,
how do you know it is a particle you are tracking? Suppose two particles are separated,
yeah.
but it is not, may not be particle, it is waves. Okay.
Well,
Only
okay.
when you measure only, it becomes
Yeah,
particle.
okay, you're right, whatever it is,
No,
you,
my question is,
okay,
anybody tracked the path far away?
yes.
I-
Okay, that's my short answer. You have this optical fiber that's moving photons, and you can see a single photon go through. All right, so now I want to put everything together and also mention some of my own work. So now we have these two really fundamental problems in physics. One is, what makes a superconductor go superconducting very high, at a very high temperature, and what's inside a black hole. I'm not going to answer either of them completely. I'm going to talk about recent progress in understanding these problems. And what's been clear to many people who thought even a little bit about these problems is you need to do EPR on a longer scale. EPR, as I've described, is for 2 electrons or 2 photons. But how about, 3 or 4 or 5 or 1 million electrons? How do they entangle, and what are the properties of such an entangled set of electrons? So many people have been asking these questions. There's been a lot of progress in understanding the nature of quantum entanglement of large numbers of particles. But my own tack on has been, well, it's always good to have a simple model, simple scenario in which you can completely solve everything. And then you can then try to understand more realistic systems. So I'm going to describe my favorite model, which happens to have my name on it, of many-particle entanglement. So actually, many-particle entanglement already appeared a long time ago in quantum physics, even before the discovery of quantum mechanics. And this is Kekulé, who was a chemist in Germany, who in 1865 proposed a structure for the benzene molecule. So the benzene molecule has 6 carbon atoms, and we know from the chemical bonding that there has to be 3 double bonds. So we only focus on that double bond, which I represent by this ellipse. And the modern understanding is that a double bond is exactly this EPR pair of the 2 electrons in certain orbital of carbon. All right, so you have 3 bonds allowed, and you have 6 atoms. How are you going to make them bond with each other? Well, this is one way of doing it. But this has a problem. If this was the actual bonding configuration, benzene would not be a perfect hexagon because this bond would be, say, smaller than this bond. It would be a distorted hexagon. So there's another one, which is this one. And so Kekulé's brilliant idea was it's both. And he said they resonate between this configuration and that configuration. Okay, as I said, this was long before the discovery of quantum mechanics. So today we would say Kekulé gave us the state of 6 electrons, which is an entangled state of 6 electrons. And the way you entangle 6 electrons is by first entangling them in pairs and then entangling the pairs in these 2 configurations. And this is in Wikipedia. He said they discovered the ring shape of the benzene molecule after having a daydream of a snake seizing its own tail. So I decided I should have my own dream, but no, I didn't actually have this dream. But now imagine that you have these electrons on a square lattice, like a chessboard, and there's snakes connecting different electrons in every random way. And this gives you the idea of what's called the SYK model. So let me give you the actual description of the SYK model. So imagine there's a bunch of positions where electrons can lie. So this could be, say, carbon atoms, if you could position them in some random locations. And there are certain electrons that are sitting on these positions. And now these electrons are going to entangle with each other. So the only restriction the SYK model predicts is that these electrons, as they quantum move around, they have to move in pairs. So for example, electron number 11 and 12 could move to sites 5 and 14. And in quantum mechanics, every such process that's allowed has a certain amplitude, a complex number associated with it. So this is sometimes called quantum tunneling. So these two electrons can tunnel to these sites, and there's a complex number associated with it. And really, there's many complex numbers. You can pick any pair of electrons, any pair of sites, and give a complex number associated with them. And there's of order n to the power 4 such numbers. So to figure out the properties of this set of electrons with these amplitudes or complex numbers associated with them, I have to solve Schrodinger, the famous Schrodinger of the dead and live cat. He has an equation. I have to solve that equation with these amplitudes. Turns out that equation is essentially impossible to solve because it's just too hard. Even the biggest computer in the world can't store all the information needed to solve this equation for more than about 50 electrons. 40 is really the most anybody can do. So you're faced with a problem. Yes, we think we know what the equations of the world are with lots of entanglement. We just can't solve them. They're just too hard. So what we realized in '93 is that you could make actually a great deal of progress in understanding what these electrons do when they're moving around in this way. If you made a simple assumption, it made an assumption that all these numbers were independent random numbers. That's really all you needed to do. And then you could understand in great detail what these electrons would do. And this is, there's been a lot of progress in '93, and all of our original predictions seem to really work out. So I won't describe that in any great detail here, but just to tell you what you get. So you have this simple model of electrons moving in pairs with random amplitudes for any allowed process. And you can solve it, and you find something we were very excited by. You find a theory of a metal, like copper is a metal, and if you want to understand how current flows in copper, you just let the electrons move one by one with hardly any entanglement. You'll get a pretty good theory. But here you find, if you take this SYK model and ask the electrons to move around, you'll find that they don't move one by one at all. They all entangle with each other in some kind of quantum soup, and it's the soup that carries current. Okay, so that's just a lot of words, but this particular idea has led to many developments, and in particular some understanding of why this strange metal in the high temperature superconductor has a resistivity that's linear in temperature. So that's what I was going to show here. Just a few more information on that. So that's in this simple model, the SYK model, but how about the actual material? That's nothing like the model I've described, but we've learned a lot from that model, which now allows us to describe what's happening here in this strange metal. So let's go to this regime called the AF insulator, where we do know what the electrons are doing. So it turns out in that regime, the electrons are in this configuration called an antiferromagnet, where half the electrons are down and the other half electrons are up, and they're arranged in this pattern like the boards of a squares of a chessboard. Okay, that's what they do when the density of electrons is, this P is 0. So when you change the density, you get the strange metal of the superconductor. So what do you do here? Well, to understand what we have seen from many experiments, that the electrons are going to entangle with each other. So how are these electrons going to entangle? Well, Phil Anderson and Bhaskaran had this brilliant idea of something we call a spin liquid. And what is a spin liquid? Well, at some simple level, it's exactly Kekule's idea applied to a square lattice, not just to one hexagon, but to an infinite lattice. So you just entangle electrons in pairs, and then you let them resonate with each other across the lattice. So this is a new type of state, because now the entanglement is really extremely long distance on the atomic scale. You could have a big crystal, and in principle, at low enough temperature, all the electrons are entangled in this spin liquid state. And where do you get superconductivity? Well, you have to remove a few of these electrons, so you get these vacancies. And now you have to imagine a situation where these vacancies move in pairs. And these paired vacancies are a type of particle called a boson, after Satyendranath Bose in 1924, who discovered this general idea of Bose statistics. And that is what's believed to lead to superconductivity. Okay, so that's a lot of words, but you have to try to make that into a real theory. And we don't really have such a good theory of all of these general pictures that I've been drawing for you. What we have made progress on a little bit in the last few years is take the ideas from the SYK model and apply them to this strange metal, the slightly higher temperature state, in the presence of a few impurities. And we find then that the entanglement in the strange metal is rather similar to that of the SYK model. All right, so that was, we get the linearity resistivity and all of that. All right, so that's the one main topic I wanted to talk about, which is how quantum entanglement has led to progress in understanding how these very important materials, these high temperature superconductors, behave. You know, it's a very practical object. I'm almost done, then you can ask questions. Not right now. It's this material you can hold in your hand, but to really understand what's going on in it, we need to really accept quantum entanglement at very long length scales. You know, the EPR thing that couldn't possibly be real is definitely real, and it's real in a natural object. Okay, how about black holes? So now let me try to give you some understanding of where did Hawking's results come from. And it's actually a simple way to understand this. Let's do the same EPR experiment, and instead of separating the two electrons between Bangalore and Delhi, let's separate them, throw one inside a black hole, and fortunately I'm outside the black hole with the other one. Okay, so this electron is going inside the black hole, but quantum mechanics says that this electron inside the black hole and the one outside the black hole are still entangled, because the horizon, you know, there's nothing special about the horizon. There's no sign there saying, danger, you're crossing the horizon. There's nothing, you won't even know you've crossed the horizon. You just passed the point of no return, but you don't know that yet. You'll only find out later when you get crushed at the center of the black hole. But for a while, very short while, you're perfectly happy, and you're still entangled with the other electron. But if I'm an observer sitting outside here with this electron in my hand, I can't call the other observer inside and ask them what's their orientation of their electron, because there's no way that person can communicate with me. They cannot send any signal to me. So there's quantum entanglement for sure between inside and outside a black hole, but Hawking's point, and not exactly in this way, was that to an outside observer, the state of the electron inside the black hole cannot be known. There's no possible experiment that tells me what this is. So it's really lost forever. It's disconnected from my known physical universe if I'm sitting outside. So as far as I'm concerned, this electron is in a random state. Okay? So I have a random state. And what is randomness? Well, I go back to the very first beginning of my lecture. Randomness is entropy. So there it is, and entropy leads to temperature. So that's in a very simple terms is the reason for Hawking's discovery by thinking about entangled EPR pairs across a black hole horizon. And in fact, here's a more faithful picture of it. There are always quantum fluctuations across the black hole horizon. And these EPR pairs will lead to entanglement between the quantum theory outside the horizon to the one inside the horizon. And the amount of entanglement we can see is proportional to the surface area because all the entanglement is happening on the surface. And so that leads to one of the most peculiar features of Hawking's result, that the entropy, this is Hawking's result, is proportional to the area of the horizon. This is very, very striking because any other object, like a cup of coffee, or anything you see in your lab, the entropy is proportional to the volume. The entropy of this gas is proportional to its volume. Yeah, this is only in the presence of such strong gravitational forces does the entropy become proportional to the area. And it's because the entanglement is really on the horizon of a black hole that's giving you this entropy. It's always there, so you can't get rid of it. You can't cool it any further. All right. No, I think I'll skip that. All right, so this was Hawking's argument, and how am I doing on time? I have about 5 minutes more. Okay. No, please, I want to finish this. I will call on you in a few minutes. All right. So we have understood at least Hawking's ideas in some very simple terms. But there's still a problem because Hawking's ideas are really telling us about what the black hole looks at from the outside, and you've got an entropy. But Boltzmann taught us that entropy is always associated with some randomness in the microscopic degrees of freedom. So what are the microscopic degrees of freedom here? Well, it's what's inside a black hole. So the real big question, which has driven research especially in quantum gravity and string theory, is how do you make these two tombstones compatible with each other? Boltzmann tells us S is k log omega. Hawking tells us S is, well, I gave you the formula. This is the temperature. I wish Hawking had written down S equals AC cubed over 4g h bar. Then we'd have a direct conflict between two famous tombstones. But anyway, how do we put these two tombstones together? And what this requires is that we have to get an analog of W, Boltzmann's W. And for a quantum system, that's something called the density of quantum states, how many states you have per unit energy interval. And so we want to find a physical system whose logarithm of its density of states is the entropy. Then these two tombstones would be compatible with each other. Okay. And is there any such theory? Well, the first time anybody found such a theory was actually string theory, but that string theory has a huge amount of symmetry, something called supersymmetry. And that leads to a result compatible with this, but it tells us that all the important states of a black hole have exactly the same energy. The low energy states are all degenerate. And this seems very, very unreasonable for any real object, because real objects don't have this huge amount of symmetry that leads to degeneracy. So can we have a theory for a generic black hole, and what is its density of states? So this is where I get a little technical, but anyway, let me just state the result. So it turns out the answer is yes. We finally have such a theory, which gives us a little more information on what's inside a black hole. And it only proceeds for black holes that have a net charge. And why is that? Well, because it turns out that for black holes with a net charge, this comes from solving the Einstein and Maxwell equations, the radial direction decouples from the angular direction. So if I want to do a theory of quantum gravity across such a black hole, I need only worry about one direction. So I have to do quantum gravity in one space and one time dimension, and that's a lot simpler than quantum gravity in 3 space and 1 time dimension. So what's going on? Well, then there's entanglement really at only one point. So to describe a black hole, or what's inside a black hole, and the entanglement in a black hole, I need a model, I need a theory of entanglement just at one point, with lots of entanglement. Do we have such a theory? Well, that's what I was telling you about. That is the SYK model. So you can now take the SYK model and study its entanglement in these gravitational point of view. And quite amazingly, you find there's a perfect agreement between the electronic model I told you about and its properties, and the properties of quantum gravity in one space and one time dimension. So I'm not going to say more about that. So a slightly tongue-in-cheek answer is that what's inside a black hole is something at least as complicated as the SYK model. It probably isn't that, ultimately, at very high energies. But if you want to learn, if you want to make Boltzmann compatible with Hawking, it's good enough. So what we learned from this, and this is where I'm getting a little technical, sorry for the formulae, you can work out this D of E for the SYK model, and it turns out that the D of E of a black hole has a very similar form. I won't go into any of the details here, but this is Hawking's result. And this correction as a function of energy came about because of the knowledge and the properties of the SYK model. And I have many lectures online if you want to know more about this. All right, so let me just conclude then, and then we open up to your questions. So I summarized a number of important discoveries in physics. No, I'm not done yet. Thank you. Thank you. Let me finish. Thank you. So I talked about entropy. Everybody knows what's entropy. Superconductivity, black holes, and how quantum entanglement unifies leads to ideas that are important for two very different physical systems. And the SYK model is this model of intense quantum entanglement in where the electrons entangle with each other so well that you can't tell them apart. And in one set of variables, it describes the electrical properties of high temperature superconductors. And in some dual set of variables, it tells us more about the interior of a charged black hole. Similarity in entanglement in these two very different physical systems. Thank you.
Does any student have any questions?
Yes, please. The students back there,
First.
who are, I know, are very eager to leave and go somewhere else. Ask a question and you can go. Wait your turn. He's the chair.
Yeah, well, again, I repeat what Subir said. Please ask questions about the topics that he covered in his lecture. So we'll give priority to those questions. And other questions we can take over during the coffee time. Yeah? If, well, until some student asks, let me start with you since he came first.
Sir, entanglement involves information traveling faster than speed of light.
No.
Well, is there any solution for that?
There's no, entanglement does not allow you to do that. No. Because there's no information. If I have my electron here, and my friend has an electron over there, I measure it. My friend in Delhi does not know I've measured it. There's absolutely no information that my friend in Delhi has.
How entanglement happens without information?
Because in the past, they were right next to each other. You had to create them very carefully. In the past, they were in the same room, they were in the same lab. That's when they got entangled. And then you just separated them. Yes, I know, Einstein was confused too, so you're in good company. Hi, Srikanth.
I have two questions. You can
Yes,
answer
please.
one or both. You mentioned it, but you didn't comment on the fact that in the solution of the SYK model, you are assuming the couplings to be random variables
Yes.
distributed in a certain way.
Yeah.
Now, in terms of all the things that you went on to talk about, what is the significance of that assumption?
Well, the way I presented it, randomness was actually just a tool. I would love to solve this model without random couplings. With a given scenario, you could take a multi-electron atom and look up somewhere what these numbers are. You get a whole series of numbers. Uh, I would love to solve it for those series of numbers. It's just too hard. So what we realized is if you just assume they're random, you can solve it. And then what I didn't discuss, this theory, the model is self-averaging. That is, with probability 1, any set of numbers you pick will have the same properties because it's just self-averaging. So randomness is just a technical tool to make progress. It's not essential.
But that itself is a non-trivial statement, right? Because there are models where the fact that these couplings are random lead to new physics.
Right. So there's quite a few models which have no randomness, which are now better understood because of the insights of this random solution. I mean, this is a common trick in computer science. If you want to, where you have to figure out traveling salesman or various NP-complete problems, you solve the random instance of it, and that tells you a lot about the typical instance. That's exactly what's happening here.
So, yeah. So the second question I had is, you talked about this entropy being proportional to the area, which is something striking, and you contrasted it with the normal behavior of it being proportional to the volume.
Yes.
But since you are talking in that context about gravitationally interacting systems, long-range interacting systems, that statement that the entropy normally would be proportional to the volume is not obvious.
Well, I would, it's a local field theory in any case. It's not, it doesn't have true, it's a local relativistic field theory, so it should obey the area law. Okay. It's not really long range in that sense.
Sir, thank you very much for your enlightened talk. I have one question that you have mentioned that current in a metal is carried not by individual electrons, but by an entangled quantum soup.
In a strange metal.
Yeah. How about our free electron theory of metals?
Yeah.
Because we have studied about the free electron theory of metals, but
Right.
in what way that free electron theory of metals is different from this quantum entanglement, quantum soup? This is what my question, sir.
Great question. That is exactly the question that's been keeping me awake for the last 25 years. But yes, so if you take a material like copper, there we go. So here's the picture. So what you said is correct. So the free electron theory applies to copper. In copper, we believe the electrons just move one by one. And then this has many consequences that you can work out, which I didn't describe. It tells you how the resistance changes with temperature. It tells you something about the specific heat and so on. And all of those work beautifully for copper. But if you take some other material, in particular this high temperature superconductor, and you go to this region here, then you find a total breakdown of the free electron theory. And you find this linear T resistivity. For example, this is not something the free electron theory can give you. And there are many, many other properties I have no time to discuss. And then, so how do we understand this? So the part I went through rather quickly towards the end is that if you take this theory of an entangled soup of electrons, at least, for the case of this very simple model, we can solve it. But now you take the simple model and make it more realistic. You actually imagine the soup is flowing around, and you ask, what are the physical properties of this flowing soup? And what we found is that it actually explains what's seen in these materials, in these strange metals of yttrium, barium, copper oxide, the superconductors. So it's the modern new materials for which you need the entangled soup. For the materials that are in your iPhone, you don't need it. Yeah. No, not quite. That's another great question. So this Cooper pair is really this pair here that undergoes Bose condensation. And that's the low temperature state. But as you heat it up, then you get more complex entanglement, which is longer range, and no Cooper pairs. That's the entangled quantum soup. So very rough answer is, yeah, this is what I spend my life on, you know. So when you're here, you get Cooper pairs. When you're here, you get an entangled quantum soup. That's a one-sentence summary of my research. Yes, free electrons here, Cooper pairs here, entangled quantum soup. Actually, this is a great idea. I'll make a slide saying that. Yes.
Thanks for the various connections. I wanted to just know from academic curiosity that
Yes.
you have used SYK model
Yeah.
to get the entropy and DFE connections.
Yes.
So suppose I had used some other model of
Yeah.
lattice gauge, cluster models or RVB or some Heisenberg models.
No, okay.
I might have got a different thing.
Yes.
Has it been studied or
Yeah,
I'm curious
absolutely.
that
This
one
is-
can do something.
This is a very, very important question. Again, the questions are wonderful. I'm just very impressed. So, right, there are many different types of entanglement. There's the RVB entanglement, there's the Kekule entanglement, and there's the SYK entanglement. And so the SYK entanglement happens to be some of the most complicated. It's, because you lose the idea of quasi-particles. Okay. So the SYK model is the simplest model, which has that particular pattern of entanglement. There are many other models which have the same pattern, not RVB, but other models. And the technical term is they all have this kind of time reparameterization symmetry at low energies. And all of those models, which is now understood, will give you the same DOV. So this is why I kind of said, I'm not saying there's actually an SYK model inside a black hole. There's a certain class of models, but, you know, I will proudly say the SYK model was the first model to give you that description. But there are now, since then, many others have been discovered which have the same, are in the same category of entanglement. Yeah, okay.
Coming to these black holes and your model, can
Yeah.
the model be used to say something about the evaporation time that takes place in the black holes?
Time.
Evaporation, can we really correlate that idea to so
I'm
that
sorry, I can't hear you.
no, you have your model
Yes.
applied to in the peripheral area of the black hole. Will it be connected to, in any way, to the evaporation time of the black hole? Yeah.
Yes, I mean, that Hawking himself computed, and that doesn't really, again, like you pointed out, doesn't depend on the microscopic structure in great detail. I mean, the SYK model so far has taught us a lot about what the black hole looks like from the outside. There's a lot of very active research, and that's not my own field of now trying to use it to understand what's really inside the black hole. I mean, what's inside the black hole is not just a soup of electrons, it's a soup of space-time itself. There's such strong fluctuation of space-time that it requires a totally different set of variables to describe it. And the SYK model and other models like it are leading to a lot of insights on that, but I'm not an expert on that. Okay.
I have a rather naive question. When we write about the entangled states of electrons or photons,
Yes.
we just take the spin part of it.
Yes.
What happens to the spatial part? It must be there. We just don't
Sure.
talk about it.
Yeah, well, I mean-
Nobody writes that spatial part. It shows that as we separate, somehow this gets disconnected and all that.
Yeah,
Could you
well,
say
I
something
mean,
about
people do, let me, I was simplifying, but you know, if you want to do a very clean, great experiment in physics, it has to be simple. So, for example, I mean, this experiment I showed you, What about the spatial part? Well, there is a spatial part there. Whoops, where did it go? Yeah, so this experiment, there's some molecule inside there that's emitting 2 beams of light. So those beams of light are going through optical fibers. They're moving. There's a theory for how light moves through optical fibers. But we know from that theory that the polarization of the light as it's going through the optical fiber doesn't change. We know that from the understanding. So you have a perfect setup here. You have a situation where as the light is moving, you only need to worry about the polarization because it's independent of where it is. So you can move it, and then you can see that there is this non-local, there's a spooky action at a distance. That's what they detected. Yeah, so that's the answer. I mean, but it's true, for electrons, that's rarely true. When you move an electron, you're giving it some angular momentum, and that will change its spin. There's some complicated coupling between them that Umesh actually studies a lot. So then it becomes, you can't do such a clean experiment. But let me assure you, we do worry about that a lot when we do the theory of the high temperature superconductors.
All right, thank you very much for all the interactions. Subir,
I thank the chair and Professor Subir. I now request Dr. H.N. Subramania for the remarks, please.
Okay. Sorry.
ಖ್ಯಾತ ವಿಜ್ಞಾನಿಗಳು ವೈಜ್ಞಾನಿಕ ಸಂಶೋಧನೆಯಲ್ಲಿ ತಮ್ಮನ್ನು ತೊಡಗಿಸಿಕೊಂಡು ಭಾರತೀಯ ಸಂಶೋಧನಾ ವಿಭಾಗದಲ್ಲಿ ವೈಜ್ಞಾನಿಕ ಸಂಶೋಧನಾ ವಿಭಾಗದಲ್ಲಿ ಬಹಳ ಉನ್ನತ ಮಟ್ಟಕ್ಕೆ ಏರಿರತಕ್ಕಂಥ ಸನ್ಮಾನ್ಯ ಸುಬೀರ್ ಸಚ್ದೇವ್ ರವರೇ ಮತ್ತು ಎಲ್ಲ ಇತರೆ ಪ್ರೇಕ್ಷಕರೇ, ಇವತ್ತಿನ ದಿನ ಅತಿ ಅಮೋಘವಾದಂಥ ಒಂದು ಸಬ್ಜೆಕ್ಟ್ ಬಗ್ಗೆ ತುಂಬ ಸುಶ್ರಾವ್ಯವಾಗಿ ಪ್ರತಿಯೊಬ್ಬರೂ ಮನಸ್ಸಿಗೆ ಅರ್ಥ ಆಗೋ ರೀತಿಯಲ್ಲಿ ತಿಳ್ಕೊಂಡಿದ್ದೀರಾ ಅಂತ ನಾನು ಭಾವಿಸ್ತೀನಿ. ಆದರೂ ಕೂಡ ಕೆಲವು ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಏನೇನೂ ಅರ್ಥ ಆಗಿರೋದಿಲ್ಲ ಇವತ್ತು. ಅವರೆಲ್ಲ ಸುಮ್ಮನೆ PUC ಅಥವಾ PSc ಈ ಥರ ಓದಿರ್ತಕ್ಕಂಥ ವಿದ್ಯಾರ್ಥಿಗಳು. ತುಂಬ ಓದಿದಂಥ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಅರ್ಥ ಆಗುತ್ತೆ, ಅರ್ಧ ಓದಿದಂಥ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ನನಗೆ ಏನೂ ಅರ್ಥ ಆಗಿರೋದಿಲ್ಲ. ನನಗೂ ಕೂಡ ಬಹಳ ಮಟ್ಟಿಗೆ ಏನೂ ಅರ್ಥ ಆಗಲಿಲ್ಲ, ಯಾಕೆಂದರೆ ಫಿಸಿಕ್ಸ್ ಈಸ್ ನಾಟ್ ಮೈ ಸಬ್ಜೆಕ್ಟ್. ಐ ಆಮ್ ಕನ್ಸರ್ನ್ಡ್ ಓನ್ಲಿ ವಿತ್ ಮೆಡಿಸಿನ್. ಆದ್ರೂ ತುಂಬ ಚೆನ್ನಾಗಿ ಇವತ್ತಿನ ದಿವಸ ಸಚ್ದೇವರವರು ನಮಗೆ ಒಳ್ಳೆಯ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ನಡೆಸ್ಕೊಟ್ರು. ಈ ವಿಜ್ಞಾನ ಎಂತಕ್ಕಂಥದ್ದು ನಿನ್ನೆ ಇದ್ದಂಥದ್ದು ಇವತ್ತಿರೋದಿಲ್ಲ, ಇವತ್ತಿದ್ದಂಥದ್ದು ನಾಳೆ ಇರೋದಿಲ್ಲ. ಸುಮಾರು 200 ವರ್ಷಗಳ ಇತಿಹಾಸವನ್ನು ನೋಡಿದರೆ ನಮಗೆ ಬೇಕಾದಷ್ಟು ವೈಜ್ಞಾನಿಕ ಸಂಶೋಧನೆ ಆಗಿರ್ತಕ್ಕಂಥದ್ದು ಅಮೆರಿಕಾ ಮೂಲದಿಂದ. ಐನ್ಸ್ಟೀನ್ ಆಗಲಿ, ಹಾರ್ವರ್ಡ್ ಆಗಲಿ, ಇನ್ನೊಬ್ಬರಾಗಲಿ ಮತ್ತೊಬ್ಬರಾಗಲಿ ಎಲ್ಲ ವಿಜ್ಞಾನಿಗಳು ಬಂದಿರತಕ್ಕಂಥದ್ದು ಅಮೆರಿಕಾ ದೇಶದಿಂದ. ಇದಕ್ಕೆ ಮೂಲಭೂತವಾಗಿ ಸಪೋರ್ಟ್ ಕೊಟ್ಟಿರ್ತಕ್ಕಂಥದ್ದು ನಮ್ಮ ಭಾರತ ಅಂತಂದರೆ ಇದ್ದಿದ್ದನ್ನು ಅದರಲ್ಲಿ ಅನುಮಾನವೇ ಇಲ್ಲ. ಒಂದು ಉದಾಹರಣೆಗೆ ಹೇಳ್ತೀನಿ, ನಾನು ಯಾವತ್ತೂ ಹೇಳಿದ್ದೆ. ನ್ಯೂಯಾರ್ಕ್ ನಗರದಲ್ಲಿ ಒಂದು ದೊಡ್ಡ ಒಂದು ಸ್ಕ್ವೇರ್ ಇದೆ, ಟೈಮ್ಸ್ ಸ್ಕ್ವೇರ್ ಅಂತ. ಆ ಟೈಮ್ಸ್ ಸ್ಕ್ವೇರ್ನಲ್ಲಿ ಸಾಯಂಕಾಲ 5 ಗಂಟೆ ಆದರೆ ಮೊದಲಿಗೆ ಲಿಫ್ಟುಗಳೆಲ್ಲ ಇರ್ತಾ ಇರಲಿಲ್ಲ ಅಷ್ಟು ಹೆಚ್ಚಿಗೆ. ಮೇಲ್ಗಡೆ ಇದ್ದಂಥ ವರ್ಕರ್ಸ್ ಎಲ್ಲ ದಡ 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 ಅಂತ ಕೆಳಗಡೆ ಇಳಿದು ಬರ್ತಾಯಿದ್ರು. ನೀವು ಯಾರನ್ನು ಕೇಳಿ ಐ ಆಮ್ ಎನ್ ಇಂಡಿಯನ್ ಬಿಟ್ಬಿಟ್ಟು ಬೇರೆ ಯಾರು ಇಲ್ಲವೇ ಇಲ್ಲ ಅಂಥ ಒಂದು ಸೈಂಟಿಫಿಕ್ ವರ್ಲ್ಡಲ್ಲಿ ಹೋಗಿ ನಮ್ಮ ಭಾರತೀಯರು ಮಾಡಿರತಕ್ಕಂಥ ಪ್ರಶಂಸೆ ನಿಜವಾಗ್ಲೂ ತುಂಬ ಅನುಕರಣೀಯ ಮತ್ತು ಶ್ಲಾಘನೀಯ. ಅವರ ಸಾಲಿಗೆ ಸೇರ್ತಕ್ಕಂಥ ಸನ್ಮಾನ್ಯ ಸಚಿದೇವರವರು ಸಹ ತುಂಬ ಗೌರವಾನ್ವಿತರಾಗಿ ನಮ್ಮ ಭಕ್ತಿಪೂರ್ವಕವಾದಂಥ ನಮನಗಳನ್ನು ನಾನು ಅವರಿಗೆ ತಿಳಿಸೋದಕ್ಕೆ ಇಷ್ಟಪಡ್ತೀನಿ. ಮತ್ತು 200 ವರ್ಷಗಳ ಕೆಳಗೆ ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಇರಲಿಲ್ಲ. ಅದೇನಾಗುತ್ತೆ ಅಂತಂದರೆ ಒಂದಿನ ಏರೋಡ್ರೋಮ್ನಲ್ಲಿ, ಬ್ಯಾಂಗ್ಳೂರು ಏರೋಡ್ರೋಮ್ ಮೊದಲು ಏರೋಡ್ರೋಮ್ ಇದ್ದಂಥ ಜಾಗದಲ್ಲಿ, ಮೊದಲು ಇದ್ದಂಥದ್ದು ಏರೋಡ್ರೋಮೇ ಬೇರೆ, ಇವಾಗ ಇರೋವಂಥ ಏರೋಡ್ರೋಮೇ ಬೇರೆ. ಮೊದಲು ಇದ್ದಂಥ ಏರೋಡ್ರೋಮ್ನಲ್ಲಿ ಅಕಸ್ಮಾತ್ ಜಮ್ಶೆಡ್ಜಿ ಟಾಟಾರವರು, ಮುಮ್ಮಡಿ ಕೃಷ್ಣರಾಜ ಒಡೆಯರು ಇಬ್ಬರೂ ಭೇಟಿ ಆಗ್ತಾರೆ. ಭೇಟಿ ಆದ ಸಂದರ್ಭದಲ್ಲಿ ಸೈನ್ಸ್ ಬಗ್ಗೆ ವಿಚಾರ ಮಾಡ್ಕೊಳ್ತಾರೆ. ಸೈನ್ಸ್ ಬಗ್ಗೆ ವಿಚಾರ ಮಾಡಿದಾಗ ನನಗೆ ಜಾಗ ಕೊಡಿ, ನಾನು ಒಳ್ಳೆಯ ಒಂದು ಸೈನ್ಸ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ನಾನು ಫಾರಮ್ ಮಾಡ್ತೀನಿ ಅಂತ ಟಾಟಾಜಿಯವರು ಅವ್ರನ್ನ ಕೇಳ್ಕೊಳ್ತಾರೆ, ಮಹಾರಾಜರನ್ನ. ಇಮ್ಮಿಡಿಯೇಟಾಗಿ 300 ಏಕರ್ಸ್ ಇವತ್ತಿನ ದಿವಸ ಏನು ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಇದೆ, ಆ ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಜಾಗವನ್ನು 300 ಎಕರೆ ಇರತಕ್ಕಂಥ ಜಾಗವನ್ನು ಮುಮ್ಮಡಿ ಕೃಷ್ಣರಾಜ ಒಡೆಯರವರು ಇಂಡಿಯನ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಸೈನ್ಸ್ಗೆ ದಾನವಾಗಿ ಕೊಡ್ತಾರೆ. ಅಲ್ಲಿಂದ ಎಲ್ಲ ಪ್ರಗತಿಪರವಾದಂಥ ಸಂಶೋಧನೆಗಳು ನಡೀತಾ ಇರೋದಕ್ಕೆ ಮೂಲ ಕಾರಣವಾದಂಥದ್ದು ನಮ್ಮ ಮೈಸೂರು ಮಹಾರಾಜರವರಿಂದ ನಮ್ಮ ಭಾರತ ದೇಶದಲ್ಲಿ. ಆಮೇಲಿಂದ ನಿಧಾನವಾಗಿ ಬಾಂಬೆನಲ್ಲಿ ಶುರುವಾಯಿತು. ಬಾಂಬೆನಲ್ಲಿ ಅಟಾಮಿಕ್ ಎನರ್ಜಿ ಆಫ್ ಇಂಡಿಯಾ ಅಂತ ಅಲ್ಲಿಂದ ಶುರು ಮಾಡಿಕೊಂಡು ಬೇಕಾದಷ್ಟು ವೈಜ್ಞಾನಿಕ ಸಂಶೋಧನೆಗಳು ನಡೆದಿರ್ತಕ್ಕಂಥದ್ದು ನಿಮಗೆಲ್ಲರಿಗೂ ಅರ್ಥ ಆಗ್ತಾನೆ ಇದೆ ಅಂತ ನಾನು ಭಾವಿಸ್ತೀನಿ. ಇಂಥ ಒಂದು ಸಂದರ್ಭದಲ್ಲಿ ಇಷ್ಟು ಒಳ್ಳೆಯ ಭಾಷಣವನ್ನು ಮಾಡಿ ಇಲ್ಲಿರ್ತಕ್ಕಂಥ ಪ್ರೇಕ್ಷಕರಿಗೆ ಬಹಳ ಮಟ್ಟಿಗೆ ಇಟ್ಸ್ ಎ ಟಾನಿಕ್ ಫಾರ್ ದಿ ಬ್ರೈನ್ ಅಂತ ಹೇಳಿದರೆ ಆಶ್ಚರ್ಯ ಆಗಲಾರದು. ಇಂಥದ್ದನ್ನು ನಡೆಸ್ಕೊಟ್ಟಂಥ ಸಚಿದೇವದವರಿಗೆ ನಿಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ನನ್ನ ಹೃದಯಪೂರ್ವಕವಾದಂಥ ಅನಂತ ನಮಸ್ಕಾರಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ನನ್ನ 2 ಮಾತನ್ನು ಉಪಸಂಹಾರ ಮಾಡ್ಕೊಳ್ತೀನಿ. ನಮಸ್ಕಾರ.
Professor Umesh to join to do the honors. Also, Shri Venkateswara Reddy. Shubhankar may please facilitate.
बहुत शुक्रिया. Thank you very much. Shukriya.
I request Dr. Y.C. Kamla to propose vote of thanks.
Yes, we are coming to the end. Listening from masters is always resourceful. It is not just resourceful, it will be delightful too. Today's lecture on quantum entanglement in nature, both the black holes and superconductors, synthesizing the macro and the micro world, was really a resourceful and delightful lecture. Sir, on behalf of National College, Indian Academy of Sciences, Bangalore Science Forum and the Academic Trust, it's my pleasure to propose vote of thanks for you. I thank President of the National Education Society, Dr. H.N. Subramania, for gracing the occasion. Thank you, Professor Umesh Wagmere, sir, for choosing National College for the academic lecture. Let us continue our association for the future programs. I thank Professor Mr. Venkateswara Reddy, sir. When I took the proposal to him, so he did not take more than 5 seconds to approve the lecture looking at the merit. So, sir, thank you very much for giving the space for all these programs. So, I thank all the office bearers of all the organizations, the National College, Bangalore Science Forum, the Academic Trust, and all other organizations. Thank you. And the many luminaries across the city have gathered here, the professors, vice chancellors, and the subject experts. Thank you, one and all. Last but not the least, it is my students and teachers. Thank you, dear students and teachers. High tea is arranged outside. Please have your snacks and tea. Thank you.